Okay, so I want to show you how to analyze the hydraulic heads between two streams. What we have at the top of the page here is a sketch of a cross-section of an aquifer between the two streams that we see here on the right and left side. So I think it's pretty clear that in this model, okay, I think it's pretty clear in this model that we have the streams here and here. The way that I've drawn it, this is an unconfined aquifer. But what I'm going to say is that we've got a confining layer that is here, and that causes the saturated thickness where flow is occurring to be uniform thickness. We still have recharge that goes through it, like so, and that results in well, we still have recharge that goes through it, and then I'm also going to say that we just truncate the aquifer here and here, and the head in the stream applies to the whole end of the aquifer. And if we do that, then that makes this 2D problem into a 1D problem where the flux just looks like that, and there's a divide right here. So this problem becomes a problem we can draw out with a conceptual model as shown below, where we have uniform thickness and recharge uniformly distributed between the streams on the two ends. These are the streams, and these are the stages of the stream H1 and H2. So this conceptual model leads to the form of the equation by defining these characteristics. The dimension is 1D, it's steady state, it's homogeneous, isotropic, there's recharge, and the aquifer type is confined. So based on that, we get that the governing equation looks like that. And now to solve this, the approach is shown here. We first developed the conceptual model, so we can check that off. Then we identified the form of the equation. The next thing we'll do is identify the boundary conditions, and then we'll solve for the heads using the constants or we'll solve for the constants using the boundary conditions. So here's the governing equation, the conceptual model, and the boundary conditions are going to be we can specify the head here at x equals 0. That is going to be the head is equal to h1, the head in the stream. And out here at x equals L, we can also specify the head, and that's that the head is equal to H2, the head in the stream over here. And you can see the way I've drawn this that H1 and H2 are potentially different. So that leads to two boundary conditions shown here for the left side and here for the right side. H equals H1 at x equals 0 and H equals H2 at x equals L. So we'll always write boundary conditions in terms of a specified head or a specified flux at a location. So to solve this problem, we're going to start with the governing equation, and then we'll integrate that twice to get an expression for the head. So if we integrate this once, we get on the left side just the gradient, and on the right side we get this term here, which is constant, times x plus a constant of integration. And then we integrate this again, and we integrate the left side, we just get the head, and we integrate the right side, we get that C1 times x plus C2. So there's an expression for the heads, and we need to then use the boundary conditions to solve for that. So I'm just going to rewrite this. And then I'm going to use the first boundary condition and substitute in, and I substitute in H equals H1, and then X equals 0. So that term is 0, that term is 0, and then that term is C2. So from this, we get that C2 is equal to H1. Then we can substitute in the second boundary condition in there. That gives us H2 equals, now we're going to substitute in X equals L. So minus R over 2 KB L squared plus C1L plus C2, but we know now that C2 is H1. So that's the expression. We know everything except C1, which is what we're after. So I'm going to subtract off H1 from both sides. And then I'm going to add RL squared over 2KB. And that's going to equal C1L. But I want to get rid of that L, so I'm going to divide through by L. And that just gives me then an expression for C1 as H2 minus H1 over L plus RL over 2KB. Okay, so let's just check the units on that. So the units of this one are dimensionless, and the units of R and K are the same, so they cancel, and L and B are the same, so that's dimensionless. So that looks okay. And then we can substitute in C1 in there, and that'll give us the result. Okay, so this is our result, where that term there is what I calculated before on the previous slide as C1. And we can get a sense for what this looks like, because this term right here, the x squared, is a parabola. The minus x squared is an upside down parabola. So this term here looks like this. The H1, that moves it up. So we then have a term that looks like that. And then this term here, this is the equation for a line. And it could have, I mean, if H1 is greater than if H2 is greater than H1, then it has a positive slope. So it would be a line that kind of looks like that. And so if we add that line, and that line, then it's like it's like this parabola that gets tipped. So it looks like this. So if I rewrite that, and I'm going to move it up a little bit. So here's the linear part, and then there's the parabola. So that's what we get for what the function looks like in general. And if I plot it up over here, then we can see what it actually looks like if you plot it in Excel. What I did was to show some different values of this ratio R over K. And the reason that I did that is because if you look up here at the expression, let me just change colors here so that I can highlight it a little bit better. But the recharge and the hydraulic conductivity both appear here and here. And so they're only appearing together as a ratio. So one of the insights that we get from this is that the control on the hydraulic heads that recharge plays is really going to, well, the recharge and hydraulic conductivity, those enter together. So we don't have to really think about what does recharge do to the heads or what does K do, but it's really the ratio. And you can think of it as how big is the recharge relative to the hydraulic connectivity. And so what I did over here to plot this was I set a value of L equals that and B equals that. And then H equals, so this one is H1 equals H2. So the heads on either side are equal. And in that case, this head here is symmetric. That's the maximum head. And you can see that's R over K of 0.001. So this is 0.001, and this is 0.025, a bit larger, and 0.005. And here's the heights in meters. So this is, we start at 25, so this is 5 meters above the stream. This is about 12 meters, and this is about 25 meters. And so that's, I think, a reasonable range. And what it tells us is that this is kind of a decent ballpark for this ratio of the recharge to the hydraulic connectivity. Okay, well, I can do that same process, but let the heads be different on either side. And that's what I'm showing down here. The heads on this side are lower than the heads on this side by 10 meters. And that gives us, you can kind of see the blue, red, and green have a similar look to them, except they're tipped a little bit. And one of the things that comes out of this it's not immediately apparent when you look at this initially is that the divide here, if the heads on the two sides are equal, the divide is always right there in the middle. But here, the divide is right here. And then on this one, you can see the divide is right there. And then on this one, the divide is there. So the divide is actually moving towards this higher head end as the ratio of recharge to hydraulic connectivity decreases. Okay, so that's kind of interesting because what it means is the groundwater divide, the location of the groundwater divide, depends on how much recharge. It depends on this ratio of recharge to hydraulic connectivity. So that's kind of an interesting insight because the groundwater divide, we might be tempted to put a groundwater divide right at the same place as a topographic divide. But here, this gives us a really interesting insight that the groundwater divide, the location of the groundwater divide, it can vary anywhere from between the two streams to moving here closer to the stream, depending upon the ratio of the recharge to connectivity. So that means that in general, the divide between the groundwater divide between two streams can it'll either be at the center or moving towards the stream with a higher head, and just where it is going to depend on the magnitude of the difference between the streams and this distance, but then also R over K. So one thing that would be kind of useful is if we could come up with an analysis of just where the divide is. And so we can do that because we can say, well, at the divide, the gradient is equal to 0. So we can go back to our analysis and determine where along the x-axis the gradient is 0. And so we can go and do that here in just a second.